Welcome to another GC Basic demonstration. This is part 12 for the Legacy 16F chip family. Let's get started. So we're going to look at using a graphical LCD or GLCD. We're going to be using I2C, and the previous video I showed how you can do what I call I2C discovery, I2C discovery, to find the devices. And that's very important. So also very important is liking, give this a thumbs up and subscribe, then let the video run all the way through without the matrix, which does not just doesn't come up in the searches. Okay, so we're on part 12. So as I said, part 11 was we're using the serial to do some I2C discovery, and that's worked really well. Now we know we've got some devices on here. We're actually going to use that GLCD now to have some fun. So I'm assuming you've got all the prerequisites of installing the software. You can program it, but therefore you have a PIC installed. You've got some LEDs, a pot, because we'll be using the pot. We won't be using the switches or the TTL. You've got the LCD, and you've got this GLCD SSD 1306 is the one that I'm using. This is the board I've got, and I've attached my GLCD into, essentially, I'll just draw some lines here. It wasn't that one, but it was in that area, and ground. I've actually put 4 connections on there, and I've connected my GLCD to that. But there's lots of other stuff you can do on there. So let's have a look. That's my board. You'll figure out why I'm not showing it on the camera in a minute. So effectively what I did, I've actually connected it to my GLCD. That's here. Pretend it's here. I've connected to RC4, RC3, and I've pulled off a ground connection and a 5-volt connection up to my GLCD. The rest of it, we won't be using. Well, we'll be using the pot, actually. Anything else? Ooh, lots of capabilities in the microcontroller. Lots of capabilities. So as I just said, I've connected up the SDA and SCL, or that's the serial data and the clock line to the GLCD. And I should really just stop the presentation there and discard that. Or I should just clarify in this slide here. I'll just edit it live just to prove that things aren't perfect. That should say GLCD as well. Let's get back. So I connected it into port C, 4 and 3. Okay, so I2C is, as I said yesterday in the previous video, open collector, and it has an open drain characteristic. That means the lines are pulled high with resistors. We'll look at those. And the 2 lines we're pulling up is the serial data line and the serial clock line. Now, I'm running this at 5 volts. Some GLCDs run at 3, just to make sure you know what voltage it is. I've got my 2 pull-up resistors fitted. How do I know? Because it's responding to I2C discovery, and I've got it connected in as shown. Ignore the chip here, by the way. That's just an old picture, okay? So we're going to send out a lot of starts, and this is the sequence. We're going to send out a lot of start conditions. Then we're going to send out an address, and it's on address 78. We'll look at that in a minute. We're going to send out masses of data, and then we're going to send out some stop. So each packet or sequence is a start, a send address, data, lots of data. There might be lots of data, and then a stop. And we're going to see that in various different programs that we're going to examine. But it's worth noting there's like a hierarchy or layers in the architecture, that your user program at the top that we've been writing you can write your own functions or subroutines, but there's also other things called converters, and we're going to look at those as well. So we're going to look at functions and subroutines and converters. And these things allow you to do, externalize and pull things into your compilation process. Your program is going to call a library, and that library is one of 125 plus libraries, GLCD library, and that will call other libraries. It will cascade through. So you don't have to know the details of what's going on, is how that GLCD is working. If it's not working, come to the forum and we'll have a look at it. But those GLCD libraries make calls to lower level libraries, and there's 26 of those, and one of them happens to be the I2C. And then there's specific capabilities that the low-level library is addressing in terms of its ability to generate a hexadecimal file for a specific chip. So these layers exist in your mind's eye. You've got a user program, a set of libraries, a set of low-level things going on, and hexadecimals. And you can replace any of these layers. You can replace the library layer, the low-level layer. You can replace the low-level layer. You can write your own solutions in that space. It's extremely flexible. But we're going to look at many of these functions. So we've set up the I2C, and we're going to review a whole load of demonstrations. We've got some primitives, we've got memory usage and what's called transactions. We're going to do some conversions, some sprites, and then we're going to look at a voltmeter. And let's be quite frank, this is all about what I've just spoken about. People writing their own capabilities based upon the primitives, a converter to do a BMP conversion. You've got sprites and customized subroutines and trigonometry, which is obviously a library, and the low-level commands. We're going to look at all of that. Let's get started. Let's get out to my desktop. I'm just going to leave that there. Press the Windows key, GCS, as for GC Studio. Hit it, go in, and then I'm going to zoom in on that for us. And I'm going to take the microchip PIC12 Plus board 2010, or I can open it by looking in my local folder. But I'm just going to click on that because I've been in there a few times before. Zoom out. Right, we're in the got our little logo. So top right hand corner, or Control B, open up the files, and there's a lot of GLCD stuff in here. Okay. We left it at 170, so let's select 180. Now, what's the characteristics of the GLCD I've got? This one, let me have a look how it's set up. It's for this type of SSD 1306 with the parameters of 64 by 32. Well, I haven't got one of those. Let me show you what I've got. Oh, the camera has moved. I've got one of those. That is 128 by 64 pixels. So let's have a look. I'm going to slide that across, this one here. 128 by 64. Control B to get rid of that. Explorer. Let's have a look. So the header is the same. I've left the header the same. It's identical. I'm not going to go there because all the changes are down here. I'm including, first thing I'm doing is including a library. And that library, GLCD.h, is if you include that, you need to specify the type of GLCD that you're going to be using. And I'm going to use a GLCD type SSD 1306. And that has the parameters of, that's equivalent of saying 128 by 64. And I need to give it an address, an I2C address. And from the previous video, we know it's sitting on 78 because we saw that during discovery. If you want to look at the details of this, essentially what this is going to do is use a load of commands like GLCD print, put some words on the screen. GLCD print at a XY location, Anobium 2025. and then you can put some stars on there, the height, the width, look, the height. Why don't I just program it? We'll have a look at what it's. I just pressed function key F5. It's just compiling it. I'm just going to shuffle around my screen so you can see everything that I'm doing. There we go. That's just that's what I expected. Low memory mode. I'll explain that in a minute. And it's doing some stuff. In actual fact, does that LED, does that little circle go off? Oh, it does. As I rotate the potentiometer, look. So look, how do we get all that on there? Let's reset the chip and we'll see what it's doing. I'll just use PIC plus to reset it. So it's got some strings on there. It's got some more words on there, versions, and then it's got primitives. It's got circles, squares, lines, text, etc. And it's reading the ADC and it's doing some logic. How does it do that? Because these GLCDs require a lot of RAM, and this chip hasn't got a lot of RAM. Now, if we were using a bigger chip with lots of RAM, we don't have to, it just works. But we have to help the compiler compile a version that supports low memory. And the compiler knows that this chip's got low memory. And so if we add in these little functions here, look, it says if the GLCD type is an SSD 1306 and it has low memory GLCD mode, there's a thing called open transaction. And there is another thing that says closed transaction based upon the same principle. Now, we know, I can tell you that this hasn't got a lot of memory in this chip. And if we look at the report at the bottom, it says here, it only used how much RAM? 478 bytes of RAM. So you're running a GLCD in less RAM than you've actually got in that chip. Let me explain. I'm going to open up a calculator. Classic calculator. We need memory. We write to the memory and then we copy the memory out to the GLCD. That's how they work. So I'm going to put it in decimal. I'll put it in decimal, standard decimal here. Okay. So I've got a 128 times 64 pixel device. And therefore on the screen I have got 8192. Divide that by 1024. I need 8K of RAM just to make this work. Well, I have only got 512 bytes. Well, that doesn't sound right. So 128 times 64. That's how many pixels there are. Oh, I remember. I can actually put 8 pixels in 1 byte. So the minimum that you would require to drive this LCD, this GLCD, is 1K of RAM. Well, we don't have 1K of RAM. We've only got 512 bytes. So how is it working? It works because the compiler is treating the y-axis, or the 64 bytes, in pages of 8 bytes at a time. And essentially the program pages through these 8 pages that it thinks exists, and it takes a number of bytes to do that. So if we have 128 times 64, divide by 8 to get it back to the pixel number, the amount of RAM that's normally required. But if we divide it into 8 pages, we need 128 bytes. And so page transaction is the capability to page through the graphics engine and the graphics memory 128K bytes at a time, but it just means it's a little bit slower. So in a low memory chip, which is automatically selected, you could do the same actually on a larger RAM device, but you wouldn't do that. It doesn't make sense. If you have a large RAM device, you can just write it directly out. It will operate faster. But on low memory devices, this is automatically selected. This low memory low memory mode is pre-selected for you, just knows to do it. You need to put these transactions around it. So think of this, a better way of showing this would be if I indent this like that. Think of it as like this, that it says a for next loop of 0 to 7 and a next here. And it's just paging through. It pages through the 8 pages and updates the screen. So this is how we get strings and constants onto the screen. That's what we saw initially. We saw the version pop up. I will indent that just for clarity. And then we have this big demonstration, which is reading the ADC. We've seen that before. Put that into a variable. Here is the page. Here is the page transactions, 8 of them. And it says print some string, add a position, print some other strings, put the chip megahertz on there. It's running at 32 megahertz. Look. Draw a string, draw some boxes, put a circle there. These are called primitives. GLCD print the ADC value. It says 198 at the moment. Draw a box, draw a string, draw an ellipse. These are ellipses. Look, that's an ellipse. And it says if the ADC is greater than 127, fill it or don't fill it. So fill the background and change some numbers. These are what's called primitives. But the concept here is that on low memory chips, like the legacy chips, the 10Fs, the 12S, 16S with very low memory, you must use open page transaction and close page transaction to get it to work. Otherwise, it just won't work. You'll just get nothing on the screen. And I can show you the pages. How can I show you the pages? I'm going to put a wait in here of 1 second. And we should see that when it refreshes the first screen, it does it 1 page at a time. And we'll see 1 page of 8 pixels and 1 page or another page of 8 pixels. Just programming it. GC Basic, that's 1 page, a second page. There's no more pages. There you go. Like conversely, if we change our code and only put in 1 page, which will be 0 to 0, 1 page, the first page is 0, we will only get that 1 page shown. So you can actually create strips effectively. Think of a page as being a strip. It will only draw that 1 strip, the first page, which is page 0. And this is not a characteristic of GC Basic. That we are some data missing, are we? We're not. We've only drawn 1 page. Great. Let's look at some other demos. That was 190. It's 190. I'm just going to do my Control F in here. GCB. Turn the filter on. Get rid of the clutter. 190. I've just selected the 190. 200. That's 200 is using a 128 by 32-bit device. You can have a look at that. Sprites. Control B. Now, this is written by Stanley. Stan wrote this many years ago, but it's a good way of showing that you can still do some quite complex graphics on this old low memory chips and on these legacy chips. So this is sprite support. Hey, that looks like, and you could write a game on that, and in here it shows you how Stan has written that program. And essentially what he's doing here, he's using his own functions called draw sprite. He's written draw sprite. Draw sprite is actually using some low-level coding to calculate the Y position of that pixel on the screen, which page it's on. It then calculates the page. It then draws it into the buffer memory that's been calculated for you. And then eventually, look at that, he draws out the pixel, and look, he opens the transaction. He then closes that transaction. So we already know that's the paging operation that he's got working. And then finally, it does an else, and it's the opposite. It overdraws what was there before. This is a worthwhile demonstration to look at to understand how you can write virtually a game in a microcontroller. But essentially, you're seeing the same paging. That was Sprites. Let's create a voltmeter. Stand right this. Same setup, GLCD, all the same. But now he's included a library called trigonometry. And it'll become obvious why he's used trigonometry, because he wants to calculate something in an arc. He defines the input for the potentiometer, a load of variables, and then he's using how many decimal points is it? Do trigonometry to 2 decimal places. And he's reading the ADC and showing it on the screen. He's drawing arcs, lines, and he's using the basis of the game before to create this look. I'm rotating the potentiometer. You can see that. I'm rotating the potentiometer, and he's built a really simple voltmeter. And that voltmeter just works. It just works, and it's sitting there in very little amount of memory. It's actually only used, if you look at that, it's used how much of the RAM? Probably a little bit less than we saw in the previous demonstration of all the circles, etc. But it's actually using 57% of a very small chip. So you could actually do a voltmeter on a very small chip, as demonstrated. $225, sorry, I've added this one in this morning. Control B. This is how you use what's called a converter. Converters are interesting because they permit you to do something like this. I'm just compiling it up to show you the result first. About to load a BMP. Not complex. Now, you saw the paging there happening. I think there's a small delay in there to see that we can see it. But that's because the paging is going on. But how does all this magic happen? Well, same header. No memory mode is turned on. Absolutely. Now, you can say hash include an Obium full BMP. Let's look at that file. I'm just opening up my set of folders, and in here there must be a BMP type. Let's have a look. There's a BMP file in my folder structure, and there it is. That is my BMP. So if I edit that, should I edit this? This could be fun. Let's do it live. Can I actually draw something in here? Oh, look at that. Now I don't, how's that going to save that as a BMP, huh? Save a copy. I need to put it in the same folder. I'm not going to be hunting around for it, so I'm just taking a folder name. I am going to put it in here. I'm going to call it anobium hack.bmp. Go back into my source program. I call it anobium hack. Now what it's doing, the converter, there's a converter. It didn't find my file because I gave it the wrong name, is my guess. Oh, that's not a BMP. Look at the size of that file. That's not a BMP. not a BMP. That's interesting. Oh, it's got color in it, look. So therefore it cannot be a BMP. A BMP is black and white. Save as. No, that's converted that to some other format. Have I got a tool in here I can open it up with? File, save as. I'm just going to save that. It's actually a PNG, just so that those who are playing along at home. I'm just actually saving it, okay. Here's the file name. ANOBI. Hopefully that saved it as a BMP. I don't think it has, that's the problem. Maybe it has, we'll have a look. No, that's not a BMP. Hence that's what we won't compile. I'll explain. I'll try once more. No, it's not a BMP. I haven't got time for that. So you can include a file of a different type, of a different extension. There is a set of converters, and you can write your own converters. It will convert a BMP into a set of GCB source. Let me compile that to show you. There's magic happening on the screen, and what that just created, and the converter creates this automatically. That's what its job is. It created a file called anobiumfull.gcb, and that's the same name as the file. And it's just created this a few seconds ago, and it creates. Okay, it's got information in here. It's got metrics. Tells you it's a 124 by 68. It's 1 bit bits per pixel, and there's a huge table. Look at that. And that table and that BMP has been created, converted into a table. This program essentially will forget about opening pages because we know about that. It reads that table in, Anobium full, we know its name, and then we increment through reading the table, reading a table of data, and we then put that on the screen using a public GLCD command called pset, and it says basically here, like, put it at the X and Y position, and if it's set it either to the background color or foreground color and just do it. And it just passes through in the for next loop, reads through at high speed, puts it on the screen. Now, because we're using paging, it is rather slower, but it still works. So you can use BMPs, JPEGs for other and other files. JPEGs are very large, BMPs being very small, it will fit in the memory that we've got available. So we can put BMPs onto the screen as well as other devices. So back to my PowerPoint, because I'm done. Big subject, huge subject in reality. So what I wanted to do is show you that you can use a GLCD in a very low memory device like this, or legacy devices still support, and you can use hardware or software I2C. If it doesn't support it, the libraries support that, because that's a low level library. You simply tell it to use software I2C. Next, we're going to look at GLCD using SPI, where I2C GLCD represents the use of I2C across a myriad of devices. And in the summary video, I'll show you the temperature gauges and all the other I2C devices working. We're going to use another GLCD SPI to represent SPI transactions on a legacy chip, which is great. I hope you enjoy. Thank you.